Organic chemistry is all about the carbon. But making carbon-carbon bonds, surprisingly, is not all that common. In today's video, we'll teach you one of the best ways to make carbon-carbon bonds. We're going to start with a negative carbon atom, a carbon nucleophile, and it's going to go attack a carbonyl. And after this video today, you'll know how to handle that in all different types of situations. Let's jump right in. We're looking at carbon atoms that have a negative charge that will go attack something. And we don't really care right now what's on that carbon, but we want a negative attacking nucleophilic carbon atom. And there are a couple of ways of getting a carbon atom like this. One way of doing that is on an alkyne, this proton is fairly acidic. So with a really good base, now it needs to be a really good base, and the one that's most common might be sodium amide, NaNH2. With a good base like sodium amide, you can pull off that proton to make what's called an acetylide. That's a negative carbon atom on a triple bond that's ready to go attack something. So that's one way of making a negative carbon atom. Another very common way of making these negative carbon atoms, these carbon nucleophiles, is to take a carbon atom on something with a good leaving group like a bromide. And if you add magnesium, metal, you can turn the magnesium inserts inside of this bond to make a magnesium bromide. You can think about this whenever you see magnesium. We think about that as being positively charged. Magnesium likes to be positive 2. And this bromine likes to be -1. So this carbon then also likes to be -1. So all of this adds up to 0. So whenever you see this, you might see something like, they might just write it all together like this, MgBr. Whenever you see this metal, think positive metal, and the carbon attached to it's a negative carbon. So this would be the same thing as if these electrons were on the carbon and it had a negative charge. So whatever's out here, we don't really care, the rest of the molecule. If you take a good leaving group like bromide, add magnesium, you can make a negative carbon atom. This is called it looks like Grignard, but it's pronounced Grignard. This is a Grignard reagent. Victor Grignard was the scientist who first discovered these. That's one way. Another way to make a negative carbon atom that could go attack something. Instead of magnesium, another way you can do this, well, you could use this magnesium powder with a bromide. You could take it with a chloride. To make a chlorine-based Grignard. It doesn't matter if this could be an iodide. So you could make all of these you can think about as the same negative carbon that could go attack. Instead of magnesium as the metal, another common way to do these sorts of reactions is to take, again, a good leaving group like a bromide, and instead of magnesium, you could also use lithium, or you might use a lithium-based reagent like butyl lithium, and that can pull off the bromide to, again, they might draw it like this, a lithium attached to that carbon. And if you see lithium, a metal like this, we think metals are positively charged, so you can think about that as lithium with a positive charge, and this carbon has a negative charge, and it's ready to go attack something. So these would be similar reagents. That Grignard, this Grignard, that Grignard, or that organolithium reagent. All of those I would think about as a carbon with a negative lone pair ready to go attack something. Now that we know how to make a negative carbon like this, either on a triple bond acetylide with a good base like sodium amide, or by making a Grignard or organolithium reagent, one common way to make carbon-carbon bonds is by allowing this Grignard or negative carbon atom to go attack a carbonyl compound. So let's pick a very simple Grignard. Let's pick maybe a 2-carbon ethyl MgBr. So I think about this like 2 carbons with the positive magnesium. I'm thinking about this having a lone pair with a negative charge ready. So this carbon atom is ready to go attack something. So that's how I'm going to consider this molecule. And let's pick a carbonyl compound like acetone. So this negative carbon atom is going to attack the most positive spot on this molecule. So think about it just for one moment. Where is the most positive spot on this molecule, on the acetone? So think about the electronegativity of all the elements. Who's pulling on the negative electrons the most? And you might think, oxygen's the most electronegative. So it pulls the negative electrons towards it. So this carbon is partially positive, and the oxygen is partially negative. So this negative thing is going to attack that positive carbon. So let's redraw that again. So here's my Grignard negative carbon. We'll draw my lone pairs on. There's my acetone. So these electrons will attack this carbon and try to make a bond between this carbon of the carbonyl and this carbon of my ethyl. The problem with that is there's already 4 bonds on this carbon atom, so trying to make one more makes 5 bonds on this carbon. I can't do that unless I can fix that problem. And one way to fix that problem is to have these electrons go up onto the oxygen, these pi electrons. So now I have my ethyl attacked down here, and now I have an oxygen with 3 lone pairs on it. So it has a -1 formal charge. So this molecule would stay like this until it would just float around in my beaker or my flask until I quenched the reaction. I would quench it. And what that means is I would come along, add a little bit of acid and water. So this negative would grab a hold of the H plus acid, and that would make an alcohol. So a Grignard attacking a carbonyl ketone like this, it's a backside attack, electrons go up, they stay up until I quench, and it becomes an alcohol. I want to focus a little bit more on this part of the reaction and see what all situations might you run into instead of just attacking a ketone like this, and how you can think about all of those situations. When a Grignard, now let's use R, negative carbon. So I don't really care what it is. It could be a methyl, an ethyl, a propyl, an isopropyl, a phenyl, whatever. But negative carbon atom. Every time you attack a carbonyl, we're going to attack the backside of that carbonyl. And always, when you backside attack that carbonyl, the electrons go up onto oxygen. After that happens, we always ask ourselves, so the electrons go up. After we attack, the electrons go up onto oxygen. After it goes up, we always ask ourselves, can they come back down? And the answer is only yes if there's a good leaving group on the carbon. So when these electrons go up onto the oxygen, if there's a good leaving group, on this carbon, then the electrons could come back down and could kick off the good leaving group. So let's look at a couple of situations. If the carbonyl has, like we saw in that last example, 2 carbon groups, so it's a ketone, these are bad leaving groups. So those are not good leaving groups. If you have, we already know that carbon groups are bad leaving groups, but how about a hydrogen and an aldehyde? That's also a bad leaving group. So those like to stick on really tightly to the carbonyl. They don't want to let go. The groups that are pretty good leaving groups, we know chlorine's a good leaving group. So if you have an acid chloride, a carbonyl with a chlorine next door, an acid chloride, that's a good leaving group. And the other one, for our case, with these carbonyl compounds, the other good leaving group is if you have an ester. So whatever, oxygen with a ethyl group or a methyl. So that would also be a good leaving group. So let's look at a couple of examples and see how we handle those. So let's make a Grignard reagent. Let's do phenyl this time. So I'm going to start with phenyl bromide. I want to make this carbon a good attacking carbon, so we'll add some magnesium. So now it's a Grignard. This carbon, this green carbon, is a negative carbon. So I can think about that like a phenyl group with a lone pair on that carbon, and it's ready to go attack something. All right, let's pick this acid chloride compound, and let's put an ethyl group, 2 carbon atoms on this side. So I have this, and I have this negative carbon, and it goes hunting. The negative carbon's looking to attack something. Where will it attack? Well, we said it will attack the backside of my carbonyl. And when I do that, the first thing I think of are the electrons go up onto the oxygen. Every time I do that, I have to ask myself, can these electrons come back down and reform this bond? The answer is yes, if there's a good leaving group. Ethyl, bad leaving group. Chlorine, that's a pretty good leaving group. So these electrons come back down from the oxygen and reform the double bond, kicking off the chlorine atom. And that makes this. So my ethyl group is attached to a carbon. The carbonyl is still there. And now attached to this carbon is this phenyl group. Okay. Plus the chlorine is left. Now, if I have a bunch of this in my beaker, an extra amount, an excess, those can go hunting again. Where would they attack? Could they attack this carbonyl compound again? Sure. They could backside attack. The electrons go up. Every time the electrons go up, I ask myself, can they come back down? Well, let's look at the 2 groups. Here I have a carbon group, ethyl. Nope, it's a bad leaving group. Here I have a carbon-based group, a phenyl. Nope, it's a bad leaving group. So the electrons will stay up on oxygen. So I start with 2 lone pairs on the oxygen. Now there are 3 lone pairs on the oxygen because the pi bond went up onto the oxygen. I have 1 phenyl group, and I have the other phenyl group that just attacked. And that oxygen, of course, has a negative formal charge because it has 3 lone pairs. It stays like that until I quench with acid and water. Somebody else might write acid and water as H3O+, the same thing. That negative oxygen grabs the H+, and I make this alcohol when I'm done. So I'm not really memorizing a whole lot, other than I'm just always attacking the carbon, letting the electrons go up, ask myself if they come back down, and if it's a chlorine, or let's pick another example, I could have done this same reaction But instead of that acid chloride, let's take O. We'll put an ethyl on the other side. It could be anything. So instead of the 6-membered ring, I'm just going to write a phenyl with a negative charge. So a phenyl Grignard. I'm thinking about it as a phenyl, a negative carbon with this. So a negative carbon with a lone pair. All right, so I'm going to attack this compound. I backside attack. Electrons go up. I ask myself, can they come back down? Ethyl is a bad leaving group, just carbon atom. Oh, but on this side, when I had the chlorine, which is an obviously good leaving group, here the OET is also a pretty good leaving group. So these electrons come back down, and they'll kick off this good leaving group, the OET. And this could be O-methyl, O-ethyl, O-propyl, it doesn't matter. O whatever, that's a pretty good leaving group. So let's draw what we made. We have our ethyl bonded to this carbon. We have our carbonyl still. Bonded to the OET is gone, but it's bonded to this phenyl ring that attacked. Now if I have an excess of this and I have more negative phenyl Grignard in there, well, it could backside attack. The electrons go up. I ask myself, can they come back down? Ethyl's a bad leaving group. Phenyl's a carbon-based thing. It's a bad leaving group. So no, they can't come back down. So they stay up on that oxygen. And I have 2 lone pairs where I start. So now I have 3 lone pairs of electrons on that. So it's got a negative formal charge. Ethyl, phenyl, and then this phenyl just attacked as well. It stays like that until I add acid and water. I quench it. That negative oxygen grabs the H+. To become this alcohol. Okay, let's do 1 or 2 more. Let's start with isopropyl chloride and add lithium. So that makes this compound isopropyl lithium, or I think about that as a negative carbon. Lithium is a positive metal, so the carbon attached to it's a negative carbon. So that I'm thinking of as a lone pair of electrons ready to go attack something. And let's pick a carbonyl with a propyl on this side and a hydrogen on this side. So this negative carbon goes hunting. And where does it attack? Well, it attacks the backside of my carbonyl. The electrons go up on the oxygen, and it starts with 2 lone pairs. The electrons go up. I ask myself, can they come back down? That's why I look at the 2 groups. Carbon-based group, bad leaving group. It's not going to come back down. That's stuck on too much. Bad leaving group. Hydrogen is also a bad leaving group, so it won't leave. So those electrons will just stay up on the oxygen. So let's draw what we make. Now I have 1 bond from carbon to oxygen. I have 3 lone pairs on it, so a negative formal charge. The hydrogen is still there. The propyl is still here on this side. And I attacked with my isopropyl, did the backside attack. It stays like this until I quench with acid and water. And I make my final product. All right, something to pay attention to. Whenever I make my Grignard reagent, these negative carbon atoms are so reactive, I have to be really careful what solvent I use. Often the solvent you use to make these is ethyl ether. The problem is, if I use a solvent that has a hydrogen on an oxygen, like any alcohol or water, then my negative carbon will go and grab an H+ right away, and it'll kill that Grignard reagent. It takes away the negative charge, puts a hydrogen on it, and I kill the reaction. I quench it too early. So I need to avoid any OH groups, or I need to avoid NH types of things, amines. Those would kill my reaction. Okay? So whenever I do this reaction, I need to make sure there is no water around. And we have techniques in order to get all of the water out. But before I do this reaction, maybe I want to take my flasks and put them in an oven and bake them for a while to get all traces of moisture away from the reaction. I want to take my solvents and make sure I've maybe added drying agents to get rid of all the water. Any trace of a drop of water can kill my reaction. So I have to be very careful with water. So I'm going to give you another example and see if we can understand this reaction. We've looked at aldehydes, ketones, acid chlorides, esters. But what about, let's pick propyl this time. Let's take propyl bromide, add our magnesium, and make our Grignard reagent. And I'm going to attack a carbonyl compound. Oh, let's put a carbon on this side. And on this side, let's make it a carboxylic acid. We haven't done that one yet. So maybe what I want to happen is this negative carbon. Maybe I want it to come attack. Electrons go up. I would ask myself, can they come back down? Is the OH a good leaving group or not a good leaving group? But it's not really a fair question, is it? Because it would never get to that situation. What I want you to notice is what's over here. Instead of attacking that carbonyl, it would more likely want to grab that hydrogen and kill this reaction. So it would just put a hydrogen on my propyl, make propane, and the reaction wouldn't go at all. So I'm not allowed to do this reaction with carboxylic acids because my Grignards don't play nice with OH groups. So it works well with esters, aldehydes, ketones, but not carboxylic acids. Okay, so that's it. Just a quick review. If you have a ketone, my Grignard would attack. Electrons go up. Can they come back down? The answer is no. They would stay up there until you quenched. If you have an aldehyde, you attack, electrons go up. Can they come back down? Carbon or hydrogen, bad leaving groups. So the answer is no. The electrons would stay up there until you quenched with acid and water. If you have an acid chloride, you attack, electrons go up. Can they come back down? Carbon's a bad leaving group, chlorine's a great leaving group. So the answer is yes. Then you'd have the R, it could attack again. My Grignard could attack again. Electrons go up. Can they come back down? Carbon, carbon, no. Now they stay up there until you quench. If you have an ester, backside attack, electrons go up. Can they come back down? OME is a pretty good leaving group. O whatever is a pretty good leaving group. They come back down, kick that off. So R prime, whatever that is. My carbonyl is still there. And now my new R group just came on. And if I have an excess of that, more of it, it could attack again. Electrons go up. Will they come back down? Carbon, carbon, nope. That's just like this first example. So the electrons stay up there until you quench. And finally, if you have a carboxylic acid, you grab that H plus, and that would kill my reaction. So I can't use any kind of alcohol or carboxylic acid. This reaction doesn't work. I think that's a good place to stop, a good entry point into how Grignards or negative carbons, that could be the negative carbon of a triple bond or just any carbon atom for a Grignard, how it backside attacks a carbonyl. I hope that was helpful. maybe leave a comment below, give me a quick like, and hey, subscribe to the channel so you can see more of these organic chemistry videos.